today. So the limit laws look like there's going to be super, a lot of formal stuff, but it really isn't too bad whatsoever. So obviously yesterday we used our calculator and the graph and the table, all that sort of good stuff, and we were kind of estimating what the limits were. Obviously, we want something a little more concrete, a little more specific, a little more exact. That's what we're going to look at today, are these limit laws. Now, it looks crazy. Don't be like, oh my gosh, I have to memorize all these. No. Okay, common sense. Obviously, if you are adding two functions together, personally, it's kind of obnoxious if you have to add two functions together, especially if there's maybe some fractions in them or they're rational, etc. You can do the limit of each one separately and then add those answers together at the end. I think the right-hand side of these equations are easier, so that's probably a lot of the way we're going to do it. Same with subtraction. You could subtract the functions, which could lead you to some algebra and some simplifying, or just do the limit of each function separate and subtract the overall final answers, okay? Same thing here. Now, see all these letters representing just a constant. Like, let's say you had 5. I don't know, 5 times the function. You can just throw the 5 out front, do the limit, and then multiply that answer by 5 at the end. So we're kind of doing the limit calculations first and applying the operations at the end is kind of how I think of it. Same thing here, multiplication, you get the gist. I don't want to FOIL this stuff together and make a big function. It seems gross. I'm going to do the limit of each function individually, and then I will multiply my answers at the very end. So, same thing with division. I don't want to have to do a quotient here. We're just going to do the limit of the top, limit of the bottom, get those answers individually, divide them out, okay? Same thing, like 6 and 7 look a little crazy. You don't see these quite as common, but we will see them today. So instead of doing raising this, figuring this to the n power, do the limit of the function, whatever that answer is. Then you could square it, cube it, whatever it asks you to do. Same thing if you have a root. Do the limit of the function first, get that answer, and do the root of it at the end. So again, looks crazy, but I'm going to do the limits really first of all the functions, and I'm going to apply the operations at the end. So I'm adding, subtracting, multiplying, cube rooting, whatever the case may be. Now this is, again, I say this all the time where I wish we really had color copy machines, because of course, there's so many things on there and they blend together. You might need to bold in or label, obviously the red curve at the top is the f function, because you can see we're going to do f and g, and these little straight minor blue are the g functions. So try to maybe distinguish that on your notes. I don't think that copied the best. Just make sure you can tell what's what there, okay? So again, what we're going to do, instead of me being oh gosh, I'm going to do no, I'm not going to put all that together. I'm going to do the limit of each one separately. So most of you, once you see this, how this plays out, you can do a lot of this in your work, in your head, the work in your head. So I'm going to do the limit, might put an M on that, of f of x first, okay? I'll do the g part in a minute. I'm going to work on the f one. Now, I can look at the picture, approaching -2, just going to label it on my x-axis here. Of course, I picked up red because f's in red. So as I approach from the left, of course, we're at 1. Approach from the right, we're at 1. So that's going to equal 1. I know that was very exciting. Okay, now I'm going to do the g part in green. Get ready for that. So I'm going to worry about the 5 at the end. Remember, if you have a constant, you can do the operations at the end. So I'm going to do 5 times the limit. X approaches -2 of the g. I should have given you a little more space here, but once you see the play, you'll just mental math it. So g, of course, is the blue. Should have picked up blue instead of green, I guess. So again, looking at the -2, I'm looking at the blue, If you're people dropping stuff, looking at the blue, guys. So again, here as we approach from the left, we're at -1. I approach from the right, we're right there at -1. So I'm going to do 5 times -1, and we're going to add our answers together. So your overall final answer, -4. 1 plus 9. So like I said, that was an extreme amount of writing for something. Now you see how it plays out. I don't need all that writing and explanation, clearly. We can do a lot of mental math. So I'm going to do the limit first when we approach 1 for the f, the red one. So again, from the left, we're getting here to 2. The right approaches 2, so I'm going to put 2 for that one. We're going to multiply. Then I'm going to do the limit for g as we're approaching 1. So let's take a look here. G as I'm approaching 1 from the left, 1 from the right. I don't like it. DNE for this guy. Because we have a jump. So what's your overall final answer? DNE, okay, because they both have to exist for me to multiply them together. How am I going to do 2 times does not exist? That's weird.
2 DNE.
Or if you're Alex, you're going to put 2 DNE. All right.
Simplified expression.
Oh boy, he's so good. Okay, quotient. As we approach 2, let's do F first. So here's 2, of course. Looking at the red as we approach 2. I mean, I'm going to have to kind of ballpark this. I'm going to say it's about 1.5.
I would also say that.
Give or take, okay, because we're estimating off the graph. Okay, so I'm going to put 1.5 for that. Now, as I look at G, approaching G at 2, from the right we're at 0, from the left we're at 0, this is a little problem. 0 under the line is undefined. So you could put undefined or you could put DNE, whatever you want to put here. Okay. And the final one. So, approaching 1, looking at F, of course, looking at F. So, of course, from the left, we're hitting up here at 2. From the right, we're hitting at 2. We already actually did that earlier. And now I'm just going to do the operation part. I'm going to cube that for a final answer of 8. So that's all the limit laws are telling you. Is you can do the limit of each expression and then do the mathematical operations at the end, which is a whole lot easier than trying to add functions and multiply them and do a whole bunch of stuff. Of course, we have to have some special limit laws, because why not? Okay, flip it, flip the page, flip the page. Now, these look kind of crazy, but I promise they're super simple. We definitely, probably the most obvious ones we're going to use a lot are these first 2. Are pretty common. So remember, C, they like to use C to represent a constant, just a plain old boring number. So to me, with all the variables, let's say if I gave you something a little more concrete, let's say, I don't know, x approaches 3. If I said, find that limit for me. Well, there's no variable on the 5, so your answer is just that constant 5. So if you equal just a number, there's no variable on there, you're just going to equal out that overall number. What else are you going to do with that? 2, you see, that one's pretty common. So let's do the limit x approaches, I don't know, 2. So this one we're going to use a lot today, okay? Clearly, of course, we just have our x here. Notice it says you end up equaling a, what value you're approaching. And maybe some of you picked up on that pattern yesterday. This is leading us to what we like to call direct substitution. Instead of me making these tables and estimating and all this stuff, you can directly substitute the value it approaches into the function. That's kind of what it's telling you in this one. Okay, we'll get to that. I'm just leading you to it. Of course, if you have a course, something like 3 you see, but not as common, but let's throw one on here. Let's say x approaches 1 of x to the 3rd. Just making something up. So again, that's the same thing of doing 1 here, 1 to the 3rd power. So again, to me, these are kind of obnoxious because it's leading you to what we're going to do at the end, what's called direct substitution. The value that you're approaching, you can just substitute it in for 1. That's what we're leading you to, really. And then the same thing here. Whatever value you're approaching, you can just substitute that in for x and do the root of it. So we're leading you to the direct substitution one. Probably the only kind of weird one is this top one, but if you're equaling a constant, there's no variable, what else are you going to do with it? It just is what it is, okay? All right, so here's the obnoxious part. Are you ready? And this is only obnoxious because it says to justify your steps. Okay, so just to give you an idea how much to write. It took me 1, 2, 3, 4 lines of work, okay? So kind of, kind of space it out. And I'm not going to write an essay on the side, but I'm going to put a little on the side, okay? So they want you to use the limit laws. So we're adding and subtracting. I'm not gonna, get crazy here. We're gonna do the limit of each expression. So limit, this is just obnoxious to write up. 2x squared minus the limit. We can put the limit on all of it. And the limit. Now, it asks you to justify your steps. I'll let you wait for a second. I don't expect you to have the limit laws memorized, what's what, but just to show you, I technically, one more, use this first and second limit laws. I put the limits on each expression, each term. So I'm just going to short and sweet for my explanation here. I'm just going to put that I did limits, sum, and difference. See, this is the obnoxious part. Okay, still working on evaluating it. Good stuff. Now, this is one of our limit laws. When you have a constant, like 2 and 3 here, you can remember, do that constant part at the end. So you can put the 2 out front, put my dramatic time symbol in there, not that you have to do that. Limit x approaches 5 of x squared. And I'm going to do the same thing here. I'm going to put the constant 3 in the front, 3 times the limit. X approaches 5 of x. And I haven't done anything with this. I'm just leaving it for right now. And again, for my very exciting justification of my steps, that is that constant, limits of a constant. Limits of a constant. I'm going to just scroll it up a little bit so I'm not clear at the bottom here so we can see in the back. Okay, moving on. Moving on. Okay, so now let me click it back here. It's like these problems. So like I've got this one here where you're putting the value in for x. That's what I'm going to do. So it's kind of like these limit laws 2 and 3, which I'll put the explanation here in a minute. So I'm going to leave the 2. I'm going to have 5 squared. I'm going to leave the 3. I'm going to put the 5 in for x. And remember, this was that first limit on the previous slide. When you have a constant term, there's no variable on the 4. It just equals 4. Okay, I'm just going to put, I'm not going to get crazy. Those were those, it's these guys. I'm just short and sweet. I'm going to put special limit laws. Special limit laws. And then we're going to calculate that out. Okay, so what is 2 times 5 squared minus 3 times 5 plus 4 for a final answer? Okay. Now, here's, I have a love-hate with this myself. Okay. Here is, but we're leading you to the y. Just, what do you get if you put 5 in here right away?
39.
The same thing.
Is that what happens usually?
That's what we're leading us to when we call direct substitution, but we got to work our way up to it. Remember, this is the obnoxious part.
Just do it.
This is the obnoxious part. We have to know the why
Okay, rock, paper,
before
scissors.
we get to the good part, the easy part. Okay, let's do another, shall we?
Let's take this chapter on the test.
All right, kind of the same thing. This one took me 4 steps again to, of course, to apply all our limit laws, etc. So again, when you have, and don't get excited, this little direct substitution doesn't work on every function. We'll talk about it. But when you have, of course, the quotient, oh gosh, I'm going to split it up. I'm going to do the limit of the top individually and the limit of the bottom. This is a really sloppy arrow. My handwriting is really bad today. I apologize for that. Okay, now my reason for that, I'm going to put limit of a quotient.
Oh, shoot.
Hopefully we can spell quotient. So again, just to show you, I'll bring it back. So I'm looking at all these crazy limit laws from the beginning. It's really I went too far. It's really that number 5, where you can put the limit on both the numerator and denominator separately. Okay, fast forward, moving on. Now, it's fun, super fun. It's kind of like the last problem, you have the sums and differences. So I'm going to put the limits really on all the terms, okay? So, and I'm probably going to have to move this up, but that's okay. of x cubed. The limit as x approaches -2 of 2x squared. The limit x approaches -2. I'm going to put -1 in parentheses, or sorry, 1, just 1. I'm getting crazy with the negatives. And I already feel like I need to move this up a little bit because I feel like I'm getting to the bottom. All right, limit on all the stuff on the bottom. Are we having fun yet? Good.
Be nice, Avery.
This is not my favorite part either. Okay. So that, of course, like I said, we had all the sums and differences. So that is, I'm just going to call it limit of sum slash diff. Now, just like the last problem, yeah, we're still going. I probably should have left you a little more room. So we are going to, of course, deal or handle, etc., these constants, which we don't have a lot. Really, I'm just kind of looking at the 2 and the 3. I'm going to put the 2 in front. I'm going to put the 3 in front. And rewrite all that stuff. Oh, God, I got to hit extend page. Okay. That's never a good sign. Okay, limit. X approaches -2, x cubed. Now, I'm going to put the 2, the constant, in front. Do you have to have the dramatic multiplication symbol? No. I just like it. And the limit of this one, just what it is. This is going to be nice. Limit 5. And again, that constant 3, I'm going to pop that in the front. And that, of course, are those constant, same reason, constant. It's this special, go back one more. It's this special one here where we're doing the constant. That's all it, I forget what number law it is, whatever. Oh man, it doesn't keep it where it's at. Yeah, limits and constant. I was going to put constant limits there.
These constant limits haunts my dreams.
With you. Okay, so now I think we can finally get an answer here, my friends, because we are going to use those special limit laws where you can just put the number now in for x. So we're going to do -2 cubed, -2 squared. What's the limit? What's this third one? The limit x approaches -2 of 1. That's just one constant term. Let's do the bottom. We're just going to get 5. And then 3, I'm going to put the -2 in. All right, let's calculate for a final answer. My reasoning, again, I'm not going to get crazy. I'm just going to put special limits laws. So very fun. Okay, calculate it out. Hit me with the final answer. You do get a fraction.
-1/11.
Perfect. Now, I know that was gross, okay? Now, I have to scroll it clear back to the top. I'm not telling it to reach. What do you think you get, my friends, if I just take -2 and pop it in for all those x's at the very beginning?
I'm going to guess -1/11.
So that is direct substitution, which is what's up next, which we all love and appreciate and enjoy, of course, way more than all of this. But direct substitution does not work on every type of function. So let's talk about that. So this is what same thing, what I'm telling you. This is, I could write this expression out. The limit is x approaches 5 of that expression. It is the same thing as just putting 5 in. I should have left a longer blank, clearly. So of course, if you calculate that out, 39. So that was the exact same thing you got as this one. Remember, we got the 39. You could just put 5 in for the x's and get 39. That is what we call direct substitution. But, there's always a but, yeah, right? So direct substitution only works on polynomial functions, which is like 2x squared minus 3x plus 4. That is a polynomial, a sum or difference of monomials, and rational functions. And remember, rational functions are written as fractions. Clearly there's other functions. Direct substitution would not work. We have other tools, methods, etc. we will use on those. But find the following limits by direct substitution. Bam. And now we're and now Alex is singing, and we're to the good stuff. Is your function a polynomial? Yes, direct substitution. Put 3 in for the x. So you're going to do 2 times 3 cubed minus 10 times 3 minus 8. Use your calculator, maybe mental math it. What do you got?
I'm negative 16. Beat it, KO.
So instead of using all the limit laws, here we are. Okay, B. Can we use direct substitution on B?
Yeah.
Yes, it is a rational function. Remember, they're not all going to work. We're getting into that. Rational function, a fraction, we can do it. So we're just going to put in -1 for the x's. So we're going to math it out. Okay. What lovely, fine fraction answer do you get for this?
Negative 4/3.
Perfect. See, everybody loves direct substitution. Me too, me too. Now, as always. Of course, like I've been telling you, we can't do everything with direct substitution, okay? We might have to do a little algebra simplification, everybody's favorite. A little algebra simplifying and lead us to being able to do direct substitution. So for instance, when you look at this, and I said put 1 in. Right now, put 1 in. What's going to happen to you? No buenos. Yeah, 0 underline, undefined, can't do it. But wait a minute, I'm not convinced that that would be the final answer if I looked at a graph or the table.
I'm convinced.
You're not convinced? Notice it says by a common factor. Well, we can simplify this fraction. We can factor and reduce. Just like I would never let you leave 6/8 on a test, I would make you reduce it. So we're going to try to simplify. So what do you see? Which expression factors, numerator or denominator?
I'm gonna guess the only one with a square.
Got it? Because it's difference of perfect squares. So I'm going to reduce or cancel out the x minus 1s. So even though it is a rational expression, we did have a little glitch before I simplified. Oh, now sweet. Got it. Final answer. 1/2. We can use our direct substitution, 1/2, 1/2.
So it's illogical, you can make it logical?
So always simplify, factor, cancel, reduce, etc. first. Plus right away I was like, I don't know if I trust that 0 under the line thing. I'm going to try to simplify. Okay, simplify. Here's the thing. You can't right now use direct substitution. Because again, if you throw 0 in for h, 0 under the line, undefined. Well, I don't fully trust that. So I'm going to try to simplify. So what's your gut instinct? What's the first thing we should do?
Do the factor out.
So use the right vocab. I'm not factoring, I'm foiling. We're going to multiply.
You know what I meant.
I knew what you meant, but you know. All right, so we're going to have 9. Do your middle terms, 3h, 3h. And then our h squared. So make sure you do the full foiling, otherwise you'll miss that 6h, okay? Clearly the 9s are going to get out of there.
And you can take an h out.
And we can take an h out. So if I reduce an h out of everything, I'm going to be left with 6 plus. That is a polynomial expression. I can use my direct substitution for a final answer of 6. Got it. So same deal on the homework.
Oh, no.
Easy. A little obnoxious because you have to use the justifying and the limit
Gonna
laws.
make us split the steps.
You have to. And then there's some that say to use direct substitution. You might do a little, factor, cancel, boil, whatever. Okay? So good, bad,